All right, doing some questions from section 4.2 on irrational numbers. So we're going to look at some statements and determine if they're sometimes true, always true, or never true. So the first one says all whole numbers are integers. So whole numbers are 0, 1, 2, 3, and so on. And integers, when you go from whole numbers to integers, what you're doing is you're adding in the negatives. So this is going to be always true. Integers are whole numbers. Well, this is going to be sometimes true. So if you choose maybe two different integers, you could say 6. So 6 is an integer and it's a whole number. However, if we go something like minus 11, well, there are no negative numbers in the whole number system, so this is false. So it is sometimes true. If a number is a rational number, then it is also an integer. So this is going to be sometimes true. If a number is a rational number, then it is also an integer. So you could choose a number that is an integer. It's also going to be rational. So 4 is a integer and it's a rational number. But if you choose something like a fraction, so an exception to this rule would be 2/3. So it is a rational number. We can write it as a fraction. If you write it as a decimal, it's a repeating decimal, but it's not an integer. So this is an exception to this rule. So it is sometimes true. If a number is an integer, then it is also a rational number. So this is going to be always true. Any integer can be wrote as a fraction, so therefore it's going to be always true. There is a number which is both rational and irrational. So this is never true. The thing that I look for to see if a number is rational is, can I write it as a fraction? Or if I switch to a decimal, is it a terminating decimal or a repeating decimal? If one of those things is true, then that means it must be rational, but you cannot have it both ways, so it's never true. So in the next example, we're looking at using a number line to order the following numbers from least to greatest, and we're going to try and do it without a calculator, but it's helpful, I think, if maybe ahead of time you went and you create your own little list of perfect squares, perfect cubes, and perfect fourths. So this is just 1 squared, 2 squared, 3 squared, and so on. Perfect cubes, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64. So we're going to use those for benchmarks, because if we're looking at the cube root of 13, so if we look at our list of perfect cubes, 8 is our 2 cubed, and 3 cubed is 27. So if we look at comparing that, the cube root of 13 must be between 2 and 3. And it would be closer to 2. So, and if you're ordering them using a number line, you don't have to be exact, we're just estimating here, so I think it's going to be a bit more than 2, so it's going to be somewhere in around here. So cube root of 13, that one's done. Square root of 18, so we know 16 is a perfect square, 25 is also a perfect square, so it's going to be somewhere between 4 and 5, and it's going to be much closer to 4. So we're going to put the square root of 18 somewhere up here. Square root of 9 is 3 on the nose. Fourth root of 27. So if we're looking at perfect fourths, we jump from 16 all the way to 81. 16 is 2 exponent 4, and 81 is 3 exponent 4. So it's actually going to be pretty close to 2. So now we've got to determine whether it is bigger than or less than the cube root of 13. And that's going to be pretty tough to do if you're estimating due to the fact that they're very close in value. We know they're both close to 2. So you may want to use a calculator for this, even though we were trying to avoid it. So if we compare the two of them, so if we go cube root of 13, we get 2.35 approximately, and if we go the fourth root of 27, 4, bring up our root button, 27, we find out that it is slightly smaller. So you can see that they're very close. It's going to be pretty tough to estimate those. So if I was to zoom in, we could move the cube root of 13 over a bit and then put the fourth root of 27 just under it. All right, and the final one is going to be the cube root of a negative 5. So if cube root of a negative number, we know that our value is going to be negative. So it's negative something, and if you're doing perfect cubes, it does not take long for it to get over 5. So 1 cubed is 1, 2 cubed is 8. So we're actually a little bit, we're closer to 8. So what that would mean is this is approaching negative 2. Maybe we think approximately 1.75 negative. If you have a calculator, once you're done estimating it, you can check it. So instead of taking the actual value of it, why don't we do negative 1.75 and let's cube it, see what we get. So we get negative 5.35, maybe negative 1.6, somewhere in around there, 1.7 maybe. So that one's going to be over here. So it's our only negative one. So if you're looking at not having to be that accurate, you would already know right away that it's the smallest one in terms of the value because it's the only negative one. So that's going to be our order: 1, 2, 3, 4, 5. 1, 2, 3, 4, 5.